In the last video, I showed you what's called the momentum impulse theorem. The momentum impulse theorem is simply the statement that, impulse is change in momentum. Big takeaway from the last video. Impulse is change in momentum. And now I'm going to show you how we can use that. 2,200 kilogram car is traveling at 26 meters per second. The car is brought to a stop. What is the average force in each of the three cases? Okay, so now when you hear the phrase average force, your brain should think impulse, because I just shared with you impulse is change in momentum, and impulse is average force times time. So your average force times time is change in momentum. And we can write that out bigger. Average force times time equals the mass times final velocity minus initial velocity, which is what I showed you in the last video. So if that last video did confuse you, here is the equation you're going to need to be able to use. Average force times time equals mass times final velocity minus initial velocity. So the question asks us for the average force in a bunch of different cases. So why don't I just go ahead and solve this equation for average force, since that's clearly what it wants. So I'll divide both sides by time, and we'll end up with average force. That gives me average force equals mass times the change in velocity, Vf minus Vi, both vectors. Paying really close attention to vectors, because as we go through this unit, vectors with momentum are going to get more important, and so I'm just making a point of noting everything that's a vector over time. All right, so situation, let's number these, situation 1, and I'll even color code. Situation 1 will be in blue. We gently apply the brakes, taking 21 seconds to stop, and we want the average force. So average force equals the mass, which is 2,200 kilograms. That's straight from the problem, 2,200 kilograms. My final velocity, if I'm coming to a stop, is my final velocity, if I'm coming to a stop, is 0, minus my initial velocity, 26 meters per second, and that happened in 21 seconds. And if I do out all the math for that equation real fast, all right, when I do out that math, I get that the average force applied to the car is 2,723, and I'm rounding newtons, and I got that it was negative. And we would expect negatives and positives to show up because we're dealing with things that are vectors. So this negative here stuck around. You might think that's a big force. Well, a car is a big thing, so that makes total sense. All right, why don't you actually pause the video and try those other two examples. You've seen this is fairly simple, and if you know the impulse momentum theorem, pretty easy to do. So why don't you pause the video, try those two, then we'll come back and do them together. All right, second problem, continuing my color coding. We'll do the second one in purple. So I'm using the same equation because they're all asking me for average force, and we already solved the impulse momentum theorem for average force. So finding average force in this second problem, mass of the car is the same, 2,200, extra 0 there, 2,200 kilograms times final velocity minus initial velocity, 0 minus 26 meters per second, divided by 3.8 seconds. And if we do that real fast, our answer is average force equals negative 15,053 newtons, if I round correctly. Now this should make sense to you that the force got bigger, because now we have a smaller time than in our first problem. And as you know, small time means big force, because you still have to apply just as much impulse, you still have to bring it to a stop. So the smaller the time, the bigger the force. Now that our time got smaller, 3.8 seconds, much smaller than 21 seconds, our force had to get a lot bigger. When our time was a lot bigger, our force was much smaller. So that's a connection you should make back to impulse. Big force, small time. Small force, big time. All right, and the final one, which I will do in, let's see, whatever this sky blue robin's egg color is. Average force is the mass, 2,200 kilograms. Final velocity is 0, minus 26 meters per second, because in every problem the car was going at 26 meters per second. Over this time, 0.22 seconds. So take a minute and predict this. Our time got smaller than in the last problem. What should our force do? It should get bigger. The smaller the time, the bigger the force you need. And that makes sense because we're hitting a concrete wall, going to be a big force. So if I take a second and do out that math, I get the average force applied was negative 260,000 newtons. Much smaller time, much bigger force. That's impulse. And that is the impulse momentum theorem. Good night.